Hello students, in this lecture we'll study what is a cyclic group. We'll understand this definition with an example and prove some theorem based on it. So let us define what is a cyclic group. A group is said to be a cyclic group if there exists an element A belongs to G group, such that each element of G can be written as an integral power of A. A group is said to be cyclic group if there is an element belonging to the group such that each element of that group can be written as an integral power of that element. That is, suppose if B belongs to the group, then and A also there is an element A belongs to the same group such that B is equal to A square M, where B is equal to A square M, where M is an integer. M is an integer here, not a natural number. You must keep in mind M is an integer. If you are defining a cyclic group, M is an integer. Power of A is an integer. It can be positive or negative. Then, if such situation holds true in a group, then that group is called cyclic group, and the element whose integral power generates the group is called generator of the group. Now, some important notes. If a cyclic group is generated by A, then we write it as G is generated by A. This is notation of cyclic group generated by A. Second is, if G is a cyclic group under the binary composition of addition, then G is called a cyclic group generated by A if there exists an element belonging to G such that an integral power of Gj, then Gj, so if each element of G is an integral multiple for binary composition addition and power for the binary composition of multiplication, right? That is, if suppose B belongs to G, then if G is an cyclic group under the binary composition addition, then there is element A belongs to G such that B is equal to n times A, and n is an integer, and then multiple for addition, binary addition, and index means power in the case of each element of G, power of A if it is cyclic under multiplication, and multiple in the case of binary multiplication. G cyclic if each element is an integral multiple of some element of G. This is cyclic. If a cyclic group is called a monic group, because this group is generated by a single element, an element is called, its other name is monic group. If G is a cyclic group of order n, then G is a cyclic group of order n, means if it's cyclic, it's generated by some element of a G, and if some element of G, and if its order is n, means the A's power and the element which generates it, whose nth power will equal to the identity element, means G will have how many elements? G will, if the order of G cyclic group is n, means G will have n elements, and the generator raised to power, the order of a group will be equal to the order of the group will also be equal to generator of the power is equal to the order of generator. If G is cyclic group of order n, then G will have how many elements? N elements. In that case, the order of group and order of the generator both will be same. In cyclic group, order of generator will be equal to order of the generator will be equal to the order of the group. This holds, always holds. If A is a generator of a cyclic group under the binary composition of multiplication, then A raised to -1 is also a generator of the same. That is, if X belongs to G, then and A is a generator of G, then X can be written as for n, and n is of order n. X is a element of G, and this is a cyclic group of order n, or any cyclic or n or any number. Then x for if x can written is for n and x not written is for -1 for -n. So what is imply? N and -n both are digits. So means a cyclic group can have more than one generator. It's not the case like that. The if identity element of a group exists, that is unique. So generator can be more than one. So from this example, we come to now. Let's go. Let's see generate a cyclic group of elements, and to show whether this is cyclic group or not. Show that the multiplicative group, this 1 omega omega square, formed by the cubic cubes of unity is a cyclic group. Cube root of unity, third root of unity, even both sides. This x cube is equal to 1, x cube minus 1 is equal to 0. So they are the solution of this equation. 1 omega omega square is a cube root of unity. You know that sum of cube root of unity is equal to 0, product of unity cube root of unity is equal to 1. So we use the property. We have read this in the complex number system. Now, solution of this problem is given. What is given? Given G is a group of cube root of unity under the binary composition multiplication, and G have how many elements? 1 omega omega square. And if 1 omega and omega square are the cube roots of unity, and we know that omega cube is equal to 1. So from this, each element of G is an integral multiple of integral power of not the multiple, integral power means under the binary multiplication power. That is omega into omega square, omega into omega square into omega cube is equal to 1. So each element of G generated by omega. So hence G is a cyclic group generated by omega and written as G. And then another question for this is example for this. Show that the group consisting of these 4 elements, which are fourth root of unity, under the binary composition multiplication is a cyclic group. Again, G is given 4 elements. These are fourth root of unity. 1 minus 1 iota square is a group under multiplication. So now iota, we know iota is equal to 1 minus 1. Iota square is equal to squaring of this minus 1. Iota cube is equal to iota square into iota. Iota square is minus 1 minus 2 minus iota, and that is 4 into iota square into iota square is equal to 1. So each element of G, iota is 4 is equal to 1, iota cube is equal to minus iota, iota square is equal to minus 1, iota is equal to iota. So each element of G generated by iota, integral power of iota generates the group G. This implies G is a cyclic group generated by. Let's see another example for the binary addition. Show that the set G of integers under addition is an infinite cyclic group generated by 1. Given is G is a set of integers which are infinite in number. So order of this is infinite. Since each n belongs to G, each element of this G can be written as n. Suppose n belongs to G, so n can be written n into 1, where n is integer. So what is generated to this group? 1 is generated for this G. Integral multiple and the by addition. And also each n can also be written as n is equal to minus n into minus 1. Minus n also belongs to. So 1 and minus 1 are the two generators for this set of integer under the binary combination of addition. So 2 generators. Now let's discuss another problem. Show that the group G under the binary combination congruent modulo 6 G, where G contains 0, 1, 2, 5 elements. Binary combination addition modulo 6, congruent modulo 6 is addition modulo 6 is a cyclic group under the binary composition of congruence model 6. This model 6 means, now let's see. What are the elements? 0, 1, 2, 5, 6. 1 can exist 1 is 1 into 1. So if we divide 1 plus 1 divided by 6, addition 1 addition model 6 plus 1 is equal to 2, 2 divided by 6 is equal to 20 is 2, 2 into 1. So 3 is equal to 1 addition model 6 3 times is equal to 3. 20 is 3, 3 divided by 6 is equal to 23, 3 into 1. 4, 1 addition model 6 4 times is equal to 4, 4 divided by 6 is equal to 20 is 4, 4 into 1. 5, 1 addition model 6 5 times is equal to 5, 5, when 5 divide 5 by 6, it is 6, 5, 5 is equal. So 0 is 1 additional 6, what is 6? 1 additional 1, 6 times, this is 6, 6 times, this is 6 into 1, 6 divided 6 is equal to 20. So these are elements that integral multiple of 1, means this G, any element n belongs to G can be written as n is equal to n into 1. So 1 is identical. Now similarly for 5. 5 is 5 into 1, 5, 5, 5 addition over 6, 5 divided by 6, that is 5, 5 into 1, 5. So this is equal to 5 addition 6, 5, 2 times, 5 addition 6, 2 times, 10. 10 divided by 6 is equal to 4, 4, 4, this is 10, 10 is 2 times 5. Now 3 is equal to 5 addition 6, 3 times, 15. 15 divided by 6 is equal to 3. 15 is equal to 3 times 5. Again 5 additional 6 4 times 20. 20 divided by 6 is equal to 2. 20 is 4 times 5. Again this is equal to 5 additional 6 5 times 25. Divided by 5 is equal to 6 divided by 1 6 is equal to 1. This is 5 into 5. 5 into 5. Now 0 is equal to 5 additional 6 times equal to 6 times is 30. 30 is 6 times 5 is equal to 3. These are elements of the units of G. When it comes to addition model 6, so each element of this is 5 times n times 5. Means this G under the model 6 is a cyclic group also generated by 15. So means we come to the conclusion that any cyclic group can have the generator is not always unique but can have more than one generator. So from this example we can conclude that G is a cyclic group G is a cyclic group have generators 1 and 5 which are relative prime to 6. Means let's go to 1 and 6 are is 1. Let's go to 1 and 5 and 6 is 1. So can have. So all the numbers less than 6 will be 6 which are related to 6 are can act as generator for any group under addition or 6. We'll see other example in the further study. Prove that 5/5 root of unity form a cyclic group under the binary composition of multiplication. So we know the nth root of unity is written as the set of n. G is a set of n. E is power 2r pi I double n. So 0 less than 2r pi I double n is equal to 0 less than r less than n. Is an abelian group under the binary composition. We have proved it in the earlier lectures. Now let's take from this we can conclude 5/5 root of unity. R will be taken n is 5 and r is 1 to 5. 0 less than equal to r is less than 5. So when you set r equal to 1, 2, 3, 1, 2, 3 here we got this set. G consists of this. These are the 5/5 root of unity. If I suppose x to be equal to 2 pi I upon 5, then which form will this roots will take? These roots will take this form. These roots will take this form, and you can see here e is for x is for x is for 2x is for x square is for 3x is equal to x is for 3. So 4x is equal to x for 4, and so is for 5x is equal to 1. So this cyclic group group of 5/5 of unity is generated by e is for x. So x. So this is cyclic group generated by e for x and W generated by x. Now another theorem, this is very important beautiful theorem. Let G be a finite group of order n. If G contains an element of order n, then G must be cyclic. If G is a finite group, if it contains an element whose order is equal to the order of a group, then the group G is cyclic. Beautiful thing, very beautiful. So we are given G is a finite group of order n. That is order G is equal to n. Let A belong to G. Let A belong to G such that order of A is also n. Let A belongs to G such that order of A is equal to n. Now what to prove now? Our aim is to prove that G is a cyclic group generated by A. And we prove that G is a cyclic group generated by A. So let us consider a set. Let's consider a set H consisting of all integral power of A. Integral power of means H has how many elements? Set of all H such that A is for R is integer. Set of all integers, integral power of A. Is a subgroup of G. If this is subgroup of G, this is subgroup of G, and order of A is n. N means this is the H is subgroup of a finite group G. So H must have finite group element. Finite means these infinite numbers are repetition of n distinct because order of is n. So this is a repetition of n distinct element of this H. So H must have n distinct because order of is n. Right? H is n, right? It is a subset of finite group. Therefore, this H is a cyclic group generated by A. That is subgroup of G generated by A. Therefore, order of H is equal to order of G into n. Generated by A, order of A is n. So, order of G is n, order of H is also n. So, this implies G is equal to H, both are generated by A, and G becomes cyclic. Now, very important note, to check whether a finite group is a cyclic or not, we have to find the order of each element of a group. If G contains an element whose order is equal to order of the group, then G is cyclic. Otherwise, G is not a cyclic group. G is not a otherwise G is not a cyclic, and also a cyclic group can have more than one generator. Thank you very much.